Here's a demonstration of dielectrics and capacitance. My capacitor is going to consist of my isolated Van de Graaff generator, which I'm subsequently going to charge up. Now, how can a single conductor, the spherical globe, for example, of the Van de Graaff generator, be thought of as a capacitor? In other words, if we think of the surface of the globe here as one of the plates on a capacitor, where is the other plate? Well, the other plate is actually at infinity. So before I do the demonstration, let me quickly do a calculation of the capacitance of an isolated spherical conductor. I'm going to go ahead and give the spherical conductor a charge Q by charging it up. So let's go ahead and calculate that capacitance first. Okay, so the capacitance of an isolated spherical conductor with charge Q. Okay, so here is my spherical conductor like so. We'll say it has a radius capital R associated with it. I give it a charge, I'll call it positive Q. And then therefore we have an electric field that is radially outwards like so from the surface of the globe. Okay, and then if we do a little bit of Gauss's law for a Gaussian surface with a radius that is greater than capital R, we would calculate the electric field is as follows. So for R greater than capital R, the electric field behaves as that of a point charge. It's this expression here. And then let's now find the potential difference between this plate, if you will, the surface of the globe, and the other plate that is infinitely far away. Once I have that potential difference, then we'll do capacitance is equal to charge divided by that potential difference. This will then give us the capacitance of this isolated spherical conductor. Okay, so we're going to go ahead and set up this integral. Okay, so what I'm going to do is I'm going to integrate then from the surface of the globe at position capital R all the way out to infinity. So position B in the calculation is going to be the potential at infinity, minus then the potential at position A, which is the potential at the surface of the globe. Okay, equals then the following integral, negative, and then from R to infinity of Q over 4 pi epsilon naught R squared dr. Okay, so potential at infinity is 0. Then on the right-hand side, we integrate negative 1 over R squared dr, which is positive 1 over R. Like so, and we do so from R to infinity. Okay, so right here is negative potential at position R equals then the following. Plug in infinity first and you end up with 0, and then minus with capital R plugged in like so. And let's go ahead and cancel out the negative signs. And then therefore this expression right here is the potential at the surface of the globe. So then therefore, if the potential at infinity is equal to 0, this is essentially also equal to the difference in potential from the surface of the globe all the way out to infinity. And we'll just take the absolute value of that potential difference when calculating the capacitance. So then therefore, capacitance very simply is Q divided by Q over 4 pi epsilon naught capital R, simplifying, and you end up with this expression. Like so. So epsilon naught multiplied by a distance here as the capacitance then of an isolated spherical conductor. Okay, at any rate, now we have the demonstration itself. Here's how I do the demonstration. This is not the greatest demonstration in the world, but it more or less gets the idea across. So I'm going to go ahead and charge up the capacitor here. I'm going to charge up the conductor in just a few moments. And then right here is an electroscope, which can then detect the electric field. Okay, this right here, however, this plastic cooler, this right here is going to be my dielectric. And what I'm going to do is take this dielectric and basically insert it here in between the space between the generator and the electroscope. When this happens, we should see the needle on the electroscope react in some manner. Basically, what it's detecting is detecting a change in the overall net electric field that is present at this location due to the generator and also due to the dielectric. Now, which situation is it, however? Is it the situation, for example, where the charge remains the same and then therefore the voltage drops? Or is it the situation where the voltage remains the same and then therefore the capacitance increases appropriately? Quite frankly, I'm not really sure exactly which situation it is because this situation is hard to control. It's hard to control because there's water molecules as water vapor here in the atmosphere of this room. Charge continuously leaks off of the surface of the globe. So you're going to see the needle react when that happens anyway. So it's a little bit difficult to see exactly what happens in this demonstration, but it is worth a shot. All right, at any rate, however, let me go ahead and charge this thing up. Like so. Okay, you can hear the generator discharging, by the way. It's already losing electrons into the atmosphere because there's water vapor in the atmosphere. So let me go ahead and place this fairly close. So let's detect the electric field like so. Let me kind of let it settle a little bit as best I can. Like so. Okay, now let's do this. Let's see the needle react some when I do. There we go, a little bit of a reaction there. There we go. Like so. Once everything settles down a little bit. Admittedly, it is a difficult demonstration to perform, but I do see a slight reaction here to the needle of the electroscope when I do place the cooler in between the space. Like so, okay? All right, admittedly not the best demonstration in the world, but you get the idea.